So for question 1, the answer is 1 over 13. For question 2, we have a box containing 7 red balls, 6 blue balls, and 4 green balls. 5 balls are randomly selected from the box. What is the probability that exactly 3 of the balls are blue? So first, we want to know the number of ways to get 5 blue balls in general. And we will count the number of balls that are in the box. How many balls are in the box? $17. We want to know in how many ways in general we can take 5 out of those 17 balls. So we will do 17 combination 5. You can either use your TI-83 calculator, or you can just Google a scientific calculator online. But it's better to use your calculator if you have it, to practice how to use your calculator. $17 combination 5, you will enter 17. Then math, then probability, then the key 3, and then 5. You can also use the combination formula, but that will take you a longer time. That is, you could also do 17 combination 5 equal to 17 factorial over 5 factorial. 17 minus 5 is 12. But if you do this, you will waste a lot of time. That's not my objective. It's not to test this computational. Here 5 times 3, take away 12. 4 here. 17, 28, 30. If you don't have a calculator, but I expect all of you to have that calculator. Without it, it is really going to become harder. So we have 6188 for the total number of ways of selecting 5 balls out of 17. The next question is, in how many ways will this selection consist of 3 blue balls, 3 blue balls, and 2 non-blue balls? Because we want 5 balls, out of which we want exactly 3 to be blue. So we should choose 3 out of the blue balls and 2 out of the blue balls that are not blue. So we want to choose 3 out of 6 blue, that is 6 combination 3, and that will be 20. And 2 out of 11, that is 11 combination 2, that will be 55. You can use your calculator to get those numbers. If you have a question, you stop me. So this will give 1100 divided by 6188. Two dice are rolled. What is the probability that the sum is less than 7? 2 dice are rolled. What is the probability that the sum is less than 7? We want to know in how many ways we can get sums when we roll 2 dice. So there are 36 outcomes. and we list the outcome with a sum less than 7, like 1, 1. Easily list this. If you add, you have 2, 3, 4, 5, 6, 7, 3, 4, 5, 6, 7, 8, 4, 6, 7, 8, 9, 5, 6, 7, 8, 9, 10, 6, 7, 8, 9, 10, 11, 12, 8, 9, 10, 11, 12. You can see that all of this number up here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Are the sum, the outcome with a sum less than 7. So we have 15 over 36. At a particular school, with 100 students, 34 play football, 23 play basketball, and 7 play both. We want to understand here that of the 37 playing football, 7 of them play basketball. Of the 23 playing basketball, 7 of them play football. So, what is the probability that a randomly selected student plays neither sport? We want to understand that neither is the opposite of all, and use the complement rule here. Neither is the opposite of all. So we'll instead work with those who play football or basketball. And the probability for football or basketball is the number of students playing football or basketball divided by the total number of students. So using the addition rule, we have number of football plus number of basketball minus 1 time number of both. That is 34 plus 23 minus 7 over 100, which is 50 over 100 equals to 0.5. So it's 0.5, but you need to explain why it is 0.5 for the answer. It was for neither. So we take the opposite and do 1 minus 0.5 to get 0.5 again. So here should be equals to 0.5. In exercise 2, we had a table that you need to complete. You complete so that the sum of the columns should be what is at the column, sum of the rows, and sum of the total. So make sure that you know how to complete those numbers in case you have a table like that on the exam. So the first question here is, find the probability that a patent selected at random is made in the United States and that it was issued to the government. So here we are using an, made in the United States and issued to the government. We will count the number of patents made in total, and then the number made in the United States and issued to the government to find that probability. So the number made in the United States and issued to the government is how many? Made in the United States and issued to the government, how many? 900 divided by the total, which is 100,000, equal to 0.009. Given that a patent was issued to the government, what is the probability that it is made in a foreign country? Here we have the given that, because sometimes you mix those two types of questions. Given that is like if it was issued to the government, what is the probability that it was made in a foreign country? So you go to given that, which is issued to the government, and you count, there are 1,000. How many of those were made in a foreign country? So you count foreign country and issued to the government, and you find 100. So then you do 100 divided by 1,000. We could also ask, given that a patent was issued to the government, what is the probability that it was made in the United States? And in that case, you will do 900 divided by 1,000. Because some of you did that instead, which was for question 1, you divided by 1,000 instead of 100,000. So question C, what is the probability that a patent was either made in a foreign country or was issued to the government? Here again, we will use the addition rule because of all. Question 2 for exercise 2. In a small college, it is known that 80% of students have a smartphone. 3 of the students are randomly selected. What is the probability that all 3 have a smartphone? All 3 have a smartphone. So we are here. All 3 have a smartphone. So the probability of having a smartphone is 80%. So you multiply 80% 3 times because they were randomly selected, so they are independent events. The second one, that none has a smartphone, the probability of a student selected at random doesn't have a smartphone is 1 minus 0.8, which is 0.2. And you do exactly the same thing, but now for the opposite. For the last question, we have at least one of them have a smartphone. At least one has a smartphone. The complement for this will be the complement, none has a smartphone. So in question B, we answer none has a smartphone to be 0.008. So we will do 1 minus 0.008 to have 0.992. Is that all? So that is it for take home problem 4. So we want to go and take home problem 5. What I did in the other class is that I would do take home problem 5 on Thursday. Or we can do take home problem 5 or start chapter 7. One solution is take home problem 4, a little of chapter 7. Take home problem 5, a little bit of chapter 7. Take home problem 5, a little bit of chapter 7. So that we shouldn't have to go fast with chapter 7. I will take about 30 minutes now to go over chapter 7, and then on Thursday we will go over take-home problem 5. So continue to practice the take-home problem 4. Probability is a little bit challenging. You need to remember the language. You need to understand it by practicing. So far, we have learned about descriptive statistics, consisting of collecting, organizing, summarizing data. And as I told you, to get to inferential statistics, we learn probability, which is chapter 4, 5, and 6. Chapter 6 was a bridge to inferential statistics. In inferential statistics, we learn how to make estimates about a parameter from a statistics. A simple example is, suppose you want to determine if a coin is actually fair. You are given a coin, a quarter, for example, and you don't know if it is a fair balanced coin. Theoretically, a fair balanced coin has a half 50-50 to get head or tail. So you may decide to toss your coin a certain number of times. If you toss your coin and you have 20 times and you have 9 heads, can you argue that this coin is not balanced, it's not fair? If you get 9 out of 20 heads, if you say this is not a fair coin, you just conclude that because it wasn't half, it's not a fair coin. I'm just asking a question. You will not conclude, right? So what if it is 13 out of 20? Will you still consider it a fair coin? We may begin to be arguing. From what point are we going to stop trusting the coin? That is the question we want to answer in this chapter, yes. It is what? Yeah, you should download it. Is that on Canvas? Are you sure? I just got it from Canvas now. Or where was I? This is Canvas. Yeah, I'm moving a little bit faster than what I found before. So, yes, that is chapter 7, under week 19. Go down, you see chapter 7. You see? Pardon? Oh, probably you cannot see. Okay, look at what I need to do. Oh, that's how we can argue. Sometimes just be patient, you know? You see people fight a lot because of lack of communication. Not that they're not communicating, but communication should be. Are you really understanding what I'm saying? Yeah, I should take those. After doing all those work, it is very easy to forget to click those things. But they do it that way because sometimes I don't want you to see it yet because I'm still working on it. So, okay, that makes it, okay, the other ones are great. So that I don't forget, let me just click now. Okay. I was like, what? So, I can start again from where I was. We know theoretically that if in a fair coin, there is 50% chance of getting head or tail. Now, somebody gives you a coin that you don't know. Maybe I give you a coin from my country, and you want to know, do they really know how to make coins? And one aspect you want to check about it is whether it is a fair coin. It's only that, okay? So that's the issue with statistics and science. Science has its own objective, but usually people misuse science and generalize it beyond what it was intended to. That country might decide that they want to make their coin in a way that is 2 to 3. So you cannot, because it's not half, publish that they don't know how to make coin there. They have their own way of making it. That is the culture behind science. So now we are assuming that a fair coin should have half head tail. So what we will do now in statistics is that we are going to toss a coin a certain number of times. If we toss a coin twice and we don't get heads, can we just conclude that this is not a fair? So it's only twice. Now we will go to 3 times. And we toss 3 times. So what I want you to see here is that the number of times you toss the coin has a lot to do in the reliability of your results. If I toss my coin 5 times, how will I not get a good result? But let's say I toss it 20 times and I get 13 out of 20. I can conclude that this is not a fair coin. Someone might say, no, why don't you toss it 50 times before you are really sure that it is not close to the parameter? So here we are going to learn what do we call being close to the parameter. What is the meaning of being too far away from the parameter? So we are going to learn about what we will call confidence interval. Interval within which we have a certain level of confidence that things are working fine. In chapter 8, we will start with, if it was a fair coin, this is how it should behave. If it goes beyond this, it's no more. So there are two essentially the same type of way of approaching the same thing, but with different method of computation. So essentially, we are going to be somewhere. We will always assume that the distribution is normal. Please don't write after this explanation, because what I'm putting on the board might not be well organized. I don't want you to have something that is confusing to you. So we want to know what is the mean. And then we want to know how far away can we go to localize the mean in an interval within which we will feel like if you are not there, then something is wrong. we will call it confidence interval. So, in dealing with confidence interval, I want to discuss estimation. An estimate, we use a statistic to make an estimation of the parameter. But can we use any statistic for that estimation? Next thing is to be able to determine what statistic is good enough to estimate the parameter. So, if you are using a specific number, like I say, half is an estimate of the probability of getting here. We call it a point estimate. That's what is here. A point estimate. If you are using a range of values, okay, I can write point estimate, a specific number used to estimate a parameter. For example, the average, we can use the sample mean. It's a specific number from our sample that we are using. The sample mean is an estimate of the population mean. We could want to use the mode, the median. In a normal distribution, mode, median, and mean are the same. Or we can speak about an interval estimate. Here we can say that the proportion of head to tail of a fair coin should be between 0.45 and 0.55, for example. That is a range between 0.45 and 0. We are going to learn how to determine it the right way, but this is just an example, what I call a range. It is a range of value used to estimate a parameter. So the properties of a good estimator are listed here. It should be unbiased. Unbiased means that its expectation is the parameter. That's a nice way to put it. That is, the expected value of your estimator should equal the parameter. Good estimator. I'm going to write examples here. It should be consistent. Consistent means the larger the sample size, the closer you get to that parameter, like we say about 2 sigma count. If you go to 10, 20, 50, you should be getting proportion that is very close to 50%. That is consistency. The larger the sample size, the closer you get to the parameter. It should be reliable or relatively efficient. Should be reliable or relatively efficient means of all estimators, it should have the smallest standard deviation. Meaning that the variation is not much, it does not change much. That is what we mean by reliable. So example, the sample mean X bar is a good estimator of mu. The sample mean is a good estimator of mu, the population mean, because what is the expectation? Anybody remember? What is the expected value of the sample mean? We did it last time. What was the mean of the sampling distribution of sample mean? Anybody remember? You know you have a mask, so you should speak louder so that I hear. Do you remember doing that? Do you remember the expectation of the sample mean? Last time we said E of x bar equals to mu, and variance of x bar equals to variance divided by n. In other words, the standard deviation of x bar was sigma over square root of n. That is what we are talking about. The fact that the expected value of the distribution of sample mean equal to the population mean makes the sample mean an unbiased estimator of the population mean. So we are going to say here is mu. And the standard deviation is sigma over square root of n. So the larger the sample size, this is the smallest of the standard deviation. The larger the sample size, the closer the average will be to the population. So making it a good estimator to the population. Also, we are not going to do all of it. The sample proportion is also a good estimator because we say the expected value of the sample proportion is the probability of success is P, the population proportion. For tossing coin, the population proportion is half. If you take all the coins tossed in the world, all the coins that have ever been tossed together, you will have half head, half tail. That is what we call by the probability of success. And now, look at the variance. If you use this guy as the variance, sum of x minus x bar square over n. When you take the expectation of this, it's not going to give you this. If we do the computation, you don't get this. I'm hesitating whether I should do it or not. Let me look at the time first. You can try to do it by doing E of s squared will be 1 over n, sum of E of x minus x bar squared. If you check that, you are not going to get 1 over n, sum of E of x squared minus 2x x bar plus x bar squared. So this is equal to 1 over n. This is E of x squared minus 2 E of x times E of x bar plus E of x squared, x bar squared. So when you do this, you are not going to get sigma square. You are going to get sigma square times n minus 1. So essentially, this is what happened. That is why we do, instead of doing s squared equals to sum of x minus x bar square divided by n, we do it divided by n minus 1. Because when you do this, E of s squared will be equal to sigma square. That's the reason why, instead of defining this variance of the sample by dividing by n, we divide it by n minus 1. So, sample variance is a good estimator of the population variance when we define it the way we have been defining. But the sample standard deviation, even if you define it well, is not a good estimator of the population standard deviation. But because sample and standard deviation are directly connected, we don't care because we will estimate it with the sample, with the variance, and then go and take the square root and feel free to work with it. Very important in computing, in estimating parameters is what we will call the margin of error. The margin of error is the maximum error of estimates parameter. For example, if I say the average age of St. Francis University students is between 10 and 40, am I right? The average age of St. Francis University students is between 10 years old and 40 years old. Do you think I'm right? Well, you don't need to do any work, right? What I'm saying is true, but is it useful? So we want to be useful by making estimates that are smaller as much as possible. So the range between 10 and 40 is 30 years range. That estimation is not useful. So in this 30 years range, we will, because the distribution is normal, approximately normal, so the margin of error is 15. So the margin of error is the maximum error of estimate. We can use it to determine how wrong we could go when we are making our estimates. So the margin of error E is the maximum error of estimate of a parameter. If you know the margin of error E, you can compute the confidence interval easily by saying that if I estimate that the proportion of heads when I toss this coin is 13 out of 12, out of 20, then the confidence interval will be that estimate that I got from the sample minus margin of error plus the margin of error. So essentially, we are going to end up with confidence interval is sample mean minus mu, minus E, less than or equal to mu, less than or equal to sample mean plus E. So an interval is, so the key here is how to get this margin of error. So the confidence level is the proportion of interval estimates. You can make a lot of interval estimates, but how many of them actually contain the parameter? The proportion of interval estimate that contain the parameter is what we call the confidence level when you choose samples of the same size. So a confidence interval is an interval estimate that is computed using a level of a confidence level. Now look at what I'm going to do. Suppose this is the distribution of sample mean. And somebody tells me that I want you to estimate the population mean with a 90% confidence level. Compute the population mean with a 90% confidence level. So that will mean that you want to be 90% confident that the interval I will get will contain the mean. Fair enough, what is the probability that the confidence interval or the interval estimate you are getting will actually have the mean? So if it gives me that confidence level, I will say that, okay, with that confidence level, if my sample mean is somewhere here, then I can move by E or move by E to some value here, which is x bar minus E and x bar plus E. The E I'm writing here is the distance. Actually, x bar minus mu is what we are estimating as the confidence interval. So, x bar minus E, I meant to say. So we want to say that mu, the absolute value of mu, x bar minus E. So that is what is here. So the margin of error is, when I say that my proportion of heads, let's say is 12 over 20, which is 0.6. What is the error I am committing? Is this difference? Is 0.1. Do we get this? If I get 12 out of 20 heads, then I am wrong by 0.1. If I get 0.4 out of, if I get 8 out of 20, then my proportion is 0.4 and the actual proportion is 5. So of this, I am equal distance from the actual parameter. So we count the difference between the parameter and the statistic you have used to estimate an error. So the margin of error, or the maximum error, is the maximum error again, is the most you can go away. So we are going to say, if I say x bar minus mu is the difference between my estimate and the parameter. The distance between what you get from the sample and the parameter should be less than this. That is how we define the confidence interval. So how are we going to actually compute it? We want to find the value of E by saying that if the confidence level is 90%, then I have 0.45 here and 0.45 here. Then here, I want to find the number corresponding, the Z value corresponding to this. I will call it Z alpha over 2, where alpha over 2 is 1 minus C divided by 2. Alpha is 1 minus C. It's this tail I'm trying to identify. This part is alpha over 2. This one is alpha over 2. So I am teaching as if you don't have calculator. Then we are going to get to calculator. And you will be like, why did we waste all this time? But it's good for you to understand a little bit of where what we will get from calculator will be coming from. So, pardon? C, confidence level. Okay, I say it without writing. Confidence level. We will call C the confidence level. If it is 90% confidence level, and we want that the distance from here, that this probability, we want this probability to be 0.9. So we come here, we have alpha over 2 here, and I will call this number Z alpha over 2. So this E should be the number of standard deviation from X bar to X minus E. So it is Z alpha over 2 times sigma X bar. So this distance from here to here, if we standardize x bar, we get 0. We standardize this number, we get z alpha over 2. Take it as simple as I told you at the beginning, z is equal to x minus mu over sigma, right? This is what we call z. Then, if we put x bar here and mu bar here, then x minus mu is equal to z x bar. I think that will make some sense. Think about the standard error formula. And now if we are dealing with the sample mean, this will be x mu bar sigma x bar. So this distance, x minus mu, I'm sorry, x bar minus mu, because we are now dealing with the sample mean, will be this. And we will call this one z alpha over 2 and sigma x bar. The question you will be asking yourself is, how do I get z alpha over 2? If z equals to 90%, z alpha over 2 here will be 0.05. Z alpha over 2 will be 0.05. And to get z alpha over 2, you will ask yourself, what is z? So the area to the left of z is 0.05. That's why you were doing those exercises. We are not, you want to just have that in mind. But I'm going to, you have this z in your textbook. There is a table about it, but most common ones are this one. If the confidence level, z alpha over 2 will be. For 90%, you have done this as homework, you have 1.645. For 95%, you will have 1.96. For 99%, you have 2.58. So you can use your calculator now to find those numbers if you like. So each time, think about, there are two tails. The middle is the confidence level. So to get the tail, subtract that confidence level from 1, divide it by 2, and do inverse normal, and you will get the z alpha over 2. Try to explain. Okay, this is on your PowerPoint, you will get this one. This is what I've been trying to explain. You can look at it here on the PowerPoint. Well, let's do one example. Let me summarize all the rough work I have done here. So if you have the confidence level, find z alpha over 2. Compute x bar, and now you will have E is equal to z alpha over 2 times sigma over square root of n. I wrote it sigma x bar here is the standard deviation of the sample mean. It was the regular standard deviation divided by square root of n. That's just what it is. And then the confidence interval will be x bar minus E less than mu than x bar. Let's do this example, then we can go. Julia enjoys jogging. She has been jogging over a period of several years, during which time her physical condition has remained constantly good. Usually she jogs 2 miles per day. The standard deviation of her times is sigma equals to 1.8. So we have sigma equals to what? 1.8. During the past year, Julia has recorded her times to run 2 miles. She has a random sample of 90 of these times. For these 90 times, the mean was 15.6 minutes. Sample mean 15.6. The mean jogging time of the entire distribution of Julia 2 miles running times. Find a 95% confidence interval for me. We have recorded 90 times that she ran. The time she took to run 90 times. And we want to say, in average, this is her average running time. We want to find the confidence interval. So, C here is 95%. C here is 95%. So we are going to find E. For 95%, Z alpha over 2 is 1.96. Z alpha over 2, sigma over square root of n, which is 1.96 times 1.8 divided by square root of 90. So this is the margin of error of Julia's running time. Which is 0.37 if you use a calculator. So the confidence interval for Julia running time will be 15.6 minus 0.37 less than or equal to mu, less than or equal to 15.6. So that tells us that the average running time of Julia is between 15.23 and 15.97. So we have learned this computation, but I didn't tell you the assumptions. The main assumption is that the distribution should be normal so far. Either the distribution is normal or sample size is large enough. To use the Z distribution, either the distribution is, but you must have sigma. We are going to discuss that next week. So when sigma is given, you can use that. Do you want to see how to use calculator to do that? Anybody want to know how to use calculator to do this? Oh, okay, let's use calculator for 2 minutes. For 2 minutes, let's use calculator. You are going to go to start, then test, then Z interval. If you are there, I cannot tell you the number because I don't have one. If you go to test, start going down, you might see somewhere Z interval. Anybody seeing it, something like that? Yeah, click that Z interval. Now you are going to have to choose between data and statistics. Data means you collected data that you will enter in L1. Statistic means you have the mean and standard deviation. So you will choose statistics. So what would it ask you on your calculator? Yes. So what do we're asking for you know what you put there. Okay, you can see. You just put those information. We are on test. We are on interval. You can look how to choose. Okay. Yeah. Any trouble? Enter those values, 95%, the confidence interval, confidence level, and calculate. Do you have an answer close to this one? Okay. We are going to learn as we go on how to use calculator to do most of this, but I have to explain to you where it comes from. Explanation looks a little bit more confusing. Okay. So we are going to do on Thursday. We will continue with this on Thursday with take-home problem 5. As we are starting now, you will be using calculator more and more. Don't forget calculator. We will be needing it. And if you have a problem how to use your calculator, just send me an email.